Warm greetings to you all. It's indeed an honor to give a presentation at ISSRF 2022. And at the outset, I would like to express my gratitude to Professor Lohia and the excellent team of organizers led by Professor Ansari and Dr. Barkha for giving me this opportunity to share some of our findings on this distinguished virtual platform today. In the recent times, we have been through a devastating pandemic due to the infectious viral disease COVID-19, but the world over the last 3 decades or so has been witnessing a pandemic of a different nature, a non-infectious one but very serious, and that arises from metabolic derangement, and that is obesity. And if the current trends persist, then it is estimated that more than 40% of the global population will become obese by the year 2030. This is a huge socio-economic burden and a major health issue for the countries because of the several comorbidities and serious health complications that are associated with obesity. At the root of obesity is the adipose tissue, and in particular, increased visceral adiposity is found to be very strongly connected with metabolic dysfunction. The adipose tissue was earlier thought to be a metabolically inert tissue with the simple function of storing excess energy, but however, there has been a paradigm shift in our concept of adipose tissue function, and now we know that this is highly dynamic, metabolically versatile, and it will not be an exaggeration if we say that the adipose tissue can control almost whole body metabolism. In conditions of obesity, it undergoes radical transformations. The adipocytes, which are the chief cells that store the excess energy, they become hypertrophied and attain a pro-inflammatory state. Our laboratory, together with collaborating teams, has been engaged into looking into this aspect of adipose tissue function, where the negative signals that are generated in the adipose tissue microenvironment in the hyperlipidemic condition, how they not only drive the macrophage infiltration into the adipose tissue, but also cause polarization of the macrophages from predominantly anti-inflammatory subtypes to chiefly pro-inflammatory phenotypes. And this leads to chronic low-grade tissue inflammation, which is one of the very inherent pathophysiologic features of insulin resistance and metabolic diseases. And this cluster of all such metabolic abnormalities, which is defined as the metabolic syndrome, it poses a great risk for type 2 diabetes, cardiovascular diseases, and several malignancies. In case of males, obesity and metabolic syndrome have been found to be strongly associated with fertility issues. With the alarming rise in obesity over the years, there has been a parallel rise in the incidence of male infertility. The impact of obesity on male reproduction has been studied in the light of the hormonal changes that are involved. It causes suppression of the hypothalamic pituitary gonadal axis, and with increased aromatization, the overactivity of the aromatase causing enhanced conversion of testosterone to estradiol. And in obese condition, there is like the entire hormonal profile undergoing alteration. It becomes hyperestrogenic, hypogonadotropic, hypogonadism. The testis, which is relatively poor in antioxidant defenses, is highly susceptible to oxidative damage, and the conditions of oxidative stress, they are one of the major contributing factors to reproductive impairment. In obesity, one of the contributing factors is the diet, and the dietary habits, they play a decisive role. It is not only the quantity of fat that is taken up, but also the quality of fat that matters. And diet which is rich in saturated fatty acids such as palmitate, they have been found to be very closely linked to heightened metabolic risk. Now we undertook this piece of work to understand how the continuous consumption of high fat diet enriched in saturated fatty acids could affect the testicular function and sperm quality in adult male mice. And for this, we subjected the different mice. We divided them into three groups, and the different groups were fed with high fat diet rich in saturated fatty acid palmitate for 3 different durations, and then we monitored the relevant parameters. With increasing duration of treatment, there was increased body weight gain in the HFT groups, and this was accompanied by increase in epididymal adipose tissue mass. The relative weights of testis and epididymis were significantly lesser in the 5-month HFT-fed mice. The circulatory levels of glucose, insulin, and that of free fatty acids were very high, and the HOMA-IR, which is the index of insulin resistance, clearly revealed that how the mice showed very high indices of HOMA-IR, particularly the group 2 and the group 3 mice. The serum testosterone level was on a declining trend, and from after the 3-month onwards, it showed significant lesser values, and in the long-term 5-month HFT fed group, it was the least. With the decline in testosterone that could lead to affecting the testicular function, we studied the testicular histo architecture in this control group and the HFT group. The control group were fed diet which is having 4.5% fat content, and the HFT group mice were fed diet having 32.5% saturated fatty acid content. The testicular histoarchitecture over the time period showed that it was undergoing drastic alterations. From 3 months onwards, distinct structural disorganization, loss of compactness of the seminiferous tubules was evident, and it showed increased vacuolization within the tubules as also in the interstitial spaces, and very prominently in the 5-month HFT-fed mice, there was considerable tubular degeneration causing almost partial to complete tubular atrophy. So this showed that how the testicular histoarchitecture was altered by HFT feeding in a time-dependent manner. The effect of HFT on sperm parameters was also adverse. It affected the sperm count, the sperm viability, as well as the motility. And in addition, the prevalence of anomalous sperms was more in case of the mice which were given high-fat diet. Different types of abnormalities in sperm head and tail structure were noticed, and they were quantified and scored. So this showed how the significant rise in the sperm anomalies occurred in a time-dependent manner. So HFT could compromise the sperm quality to a significant manner. When we saw the pro-oxidant-antioxidant balance, we first checked the intracellular reactive oxygen species accumulation in the testicular germ cells with the cell-permeable probe TCFTA, and it showed very high accumulation of ROS content in the HFT group. This was accompanied by upregulation of NADPH oxidases, which are the major cytoplasmic sources of reactive oxygen species. While SOD activity was high, catalase, the key hydrogen peroxide metabolizing enzyme besides GPX, showed strong inhibition. And the master transcription regulator of NRF2, when we checked its protein expression, we could find that NRF2 expression was down-regulated in the HFT group, and the negative regulator KEAP1 showed a high expression, showing that NRF2 activation was affected by HFT feeding. The HO1 and the downstream catalase expression was also severely downregulated, indicating conditions of oxidative stress in HFT-fed groups. The tunnel assay revealed presence of dark brown stained apoptotic cells in the HFT group, and this was accompanied by the increased expression of pro-apoptotic proteins and downregulation of anti-apoptotic protein, and the cleaved forms of the caspases also reveal that how the intrinsic pathway of the apoptosis, mitochondrial intrinsic pathway of apoptosis was getting triggered. The cytochrome C release from the mitochondria into the cytoplasm was clearly noticeable, as also the APAF1 expression, which was manyfold upregulated in case of the HFT mice. So this showed that how long-term HFT could trigger the intrinsic pathway of apoptosis in testicular germ cells. So with the high-fat diet treatment causing testicular dysfunction that was mainly arising from oxidative stress and that affected the NRF2 KEAP1 HO1 axis, and at the same time there was increased expression of the NADPH oxidases, resulting in more accumulation of reactive oxygen species that created conditions of oxidative stress, and this was also accompanied by deregulation of apoptosis in the testicular germ cells. Now this work was published in the Journal of Cellular Physiology, and we further wanted to check that whether if the dietary habit is changed, then can we reverse this damage? The Mediterranean diet is known to have beneficial effects, though much of the molecular mechanisms are not clearly understood. And the Mediterranean dietary pattern, it uses very sparsely the saturated fatty acids, but rather is mainly enriched in monounsaturated fatty acids, and majorly it involves olive oil, whose principal component is the oleic acid. So we now gave a subset of HFT mice olive oil based diet. So this is like having a model where there is a dietary shift from a high-fat diet that is rich in saturated fatty acid palmitate. We shifted the mice to a diet that is rich in monounsaturated fatty acid and olive oil. So this showed that the testicular histoarchitecture was the changes which were occurring in the HFT mice could be recovered to a much significant extent in case of the HFT plus OD fed group. This was accompanied with revival of the antioxidant capacity, as is evident by decreased expression of the NOX4 enzymes and the increased expression of NRF2 HO1 KEAP1 in NRF2 NQO1 HO1 catalase axis. So this showed that how this NRF2 was getting activated, and that could result in heightened expression of catalase, so it sort of could revive the antioxidant capacity. This was evident with lesser accumulation of reactive oxygen species in the testicular germ cells of HFT plus OD fed group. The nuclear localization of NRF2 that was visualized with the help of immunofluorescence also corroborated this. In the HFT fed group, while it showed that the NRF2 activation was not there in the nucleus, in the HFT plus OD fed group, the merged images can clearly show the cyan color, showing how NRF2 is getting localized in the nucleus and getting activated. So the FITC tagged antibody for NRF2, and the counter staining was done with DAPI, and this result also strengthens the result that we obtained from the immunoblotting, clearly showing the activation of NRF2 in the mice which were fed with olive oil based diet. And also, the olive oil based diet could check the apoptosis in case of the HFD feeding mice where we had observed significant deregulation of apoptosis. There was, in case of the OD fed group, there was much lesser expression of the pro-apoptotic proteins and increased expression of anti-apoptotic protein, and the entire panel here could clearly show that how apoptosis was checked in case of the HFD fed plus OD fed mice. The tunnel assay also reflected the same trend. So, taken together, the data revealed that loss of reproductive function in obese insulin-resistant mice could be recovered to a significant extent by the administration of olive oil-based diet, and therefore dietary shift to monounsaturated fatty acid is a healthy option. The work that I presented here is part of the thesis work of Shongita Ghosh. Shongita worked as a national fellow for her PhD program. She has been awarded the PhD degree and now she is working as D.S. Kothari postdoctoral fellow. Shomodi Basu is presently pursuing his PhD program and is working as a project fellow in the SERP project. The financial assistance from UGC Government of India and Science and Engineering Research Board Government of India is gratefully acknowledged, and I would also like to thank the head Department of Zoology, Vishwabharati, for providing all the necessary infrastructural facilities to carry out this work. With a warm invitation to all of you to come and visit my beautiful place, Shantiniketan. Thank you all for your kind attention. Thank you.